Okay, so welcome back to another video. So here we have an alternating sum where we have our index starting with n is equal to 1 to infinity and m is equal to 1 to infinity of negative 1 to the power n plus 1 divided by m times n squared plus m times n plus m squared times n. So there's a lot going on here, as you can see. Of course, being a double sum from one, there's a lot to compute and play around with. But for one, we can actually rewrite some things with, using some integral properties. And of course, there are a bunch of special functions that will be involved and a bunch of series representations that also will be involved with evaluating this entire series. So nothing too much of a big deal here. It may look a little bit crazy here, but actually it does come down to at least to a nice result in the end. So with that, let's actually just jump right in. Here's something to note from our denominator, because as you notice that we can actually factor out m times n of the entire denominator expression. So putting this aside, then it means we have, so keep the index the same, n is equal to 1, and then m is equal to 1 after that. So factor out the m times n, and so this will yield us m plus n plus 1. And then this is still the same for the numerator, so nothing has changed for that. So we notice that if we pay attention, m plus n plus 1, it's actually can be written in the form of an integral. So let me actually put this on the top over here. So 1 divided by m plus n plus 1 is the same thing as written as the definite integral from 0 to 1 of x to the power n plus m. Well, m plus n, however you want to put the notation, naming convention wise. So with this integral over here that we wrote down, so now we can actually rewrite this double sum. So same thing over here. So now I'll have negative 1 to the power n plus 1 divided by m times n. Then we can just substitute this for the integral over here, 0 to 1 of x to the power m plus n and then dx. So with this, now what I can do is let's actually just interchange and put the integral out first and the double sum, and we'll separate everything else so that it's with its respective index. So the sum will correlate with n, and then another sum will correlate with m. And with this, you'll also notice that this actually gives out a nice Mclaren series representation over here. What does it come down to? Let's analyze that for a sec after we write this down. So we have 0, 1, then now we have the negative. Since I also factor out the 1 from the exponent, so it's a negative 1 times the negative 1 to the power n, and then leave that outside the sum notation. So now we have n is equal 1, then negative 1 to the power n, then multiplied by x, then x to the power n, and then divided by n. And I now multiply this with the infinite sum with m is equal 1 of x to the power m, and then divided by m, then multiply with dx. So with this, you'll notice that, as I said, this actually has, both of these has a nice Mclaren series representation. And what it comes down to is that we have the integral from 0 to 1 of the natural log of 1 plus x multiplied with the natural log of 1 subtract x, then multiplied with dx. So now we're here, what can we do from here? Let's actually perform a little u substitution. I'll let u equals 1 minus x. And so from here, that means du is going to equal negative dx. So of course, you'll notice that I'll have to divide the negative to both sides, so I get a standalone dx on its own. And then now with this in hand, now let's actually change our bounds since we're now in the world of u. So our new integral here is going to be now, so if I plug this in for 1, so the top bound is going to be a 0, then the lower bound, that's going to be a 1. Then as you can see that we have to interchange this to become a negative so that the bounds actually make sense. So, but let's take things one step at a time. So now we have ln, so I have a 1 minus x, so to substitute this back in, so we're going to put this as 2 subtract u, then multiply with ln of u du to fix this up a bit. So now change the bounds, so I guess I forgot this is supposed to be times negative du. Then now interchange the bounds, so I have a 0 to 1, that becomes negative, but then that negative cancels, so it's ln of 2 subtract u, multiply with ln of u, and then du. So that's nice. So this may actually look a little bit deceiving from here. So we have a multiplication of natural logs, but different inputs, so it doesn't look like we can, go any further from here. But what's nice is that this is actually can be written in a special, clever technique. Not really special, but it's nice. So we have ln, so I'll put a 2 multiply with 1, and then subtract u divided by 2. So you can probably see where I'm going with this, that you can actually apply some natural log properties that separate this out, which is indeed the next step we're going to do. So putting this out, I have a natural log of 2 and then multiply with a natural log of 1 minus 1 over 2. So of course, natural log of 2 can come outside of that since that's a constant for 1, as we multiply it through. So first I have natural log of 2 multiplied with the integral from 0 to 1 of ln of u du. And I'm going to write this in the next line. And then add this with now, yeah, this is fine. We can't factor this out because there's a variable. So now it's ln of 1 subtract u divided by 2, and then multiply with ln of u du. Okay, so let me just highlight what we have so far to our workload. So this is what it's come down to from our double sum that we started with, and then coming down to where we're at with this sum of integrals. So now with this in mind, you can see that ln of u, the integral of ln of u, can be easily done by using integration by parts. So putting this back, so I have now the integral, well rather now ln of 2, and then multiply with, now let me put this in like the brackets over here. So I have, performing this, u times ln of u, subtract u from 0 to 1. Okay, but notice that if I plug 1, so this is 0 and then minus 1. And if I plug in 0, but notice that I have an ln of 0 over here, which is undefined, but no worries, we can fix that since we can convert this into an indeterminate form of rational functions. Then if that's the case, then we actually can apply L'Hopital's rule to get that the entire thing, or rather this entire value over here in the brackets, is going to equal -1. Okay, and so from here, now that's out of the way, so we now have to deal with what this is going to come down to, this integral. So we actually apply a little bit of the Mclaren series over here, so saving all that step and getting to the grind of it. So this is going to be, and then do some little bit of factorization out. Then we're going to have that this is this infinite sum from 1 divided by 2 to the power n, multiply with n, then multiply with the integral from 0 to 1 of u to the power n, then multiply by ln of u, and then du. So as we see from here, we're going to actually have to evaluate this by yet again applying integration by parts. So we have a negative ln of 2 here, and then we have this definite integral we need to calculate, but again apply IBP, integration by parts. And so now, so we have the infinite sum yet again, that has not changed yet. So we have 1 divided by 2 to the power n, then multiply by n. Then with this, now we have u to the power n plus 1, and then divided by n plus 1, and then multiply with ln of u. Evaluate this from 0 to 1. Okay, so that's part of it. So we also have to deal with the one with the integral minus integral of u dv, and then distribute that sum over here. So now that'll give us, so that's going to be a plus. Okay, so the same infinite sum, n is equal to 1 of 1 divided by 2 to the power n. So that's straightforward, that if you do some factorization from there, so it's n, then I can actually factor out the n plus 1 after applying that. If you let v equals ln of u, then dv is 1 over u du. dw, we're just using a different naming convention from over here, that be u to the power n, then integrate that, so it's u to the n plus 1 divided by n plus 1, factor that out, so it's an n plus 1 over here. And if I'm going too fast, you can actually try to validate this yourself, and I apologize for the speed. So 0 to 1, then now we have u to the power n, and then du, which is indeed an easy definite integral to calculate from here. And so simplifying everything out here, so I'll have negative ln of 2. What this comes down to, yet again, we have ln of 0, which is undefined, but if you do the same thing again with the whole indeterminate form, then get it using L'Hopital's rule and all that, taking the limit of it, then we're going to get that this entire thing is going to approach 0. And so that actually vanishes, and so we're left with this, and then just calculate the definite integral over here. So now that just leaves us with now negative ln of 2, add this with the infinite sum, n is equal to 1 of 1 divided by 2 to the power n, then times n multiplied by n plus 1, and then square. What's nice is, now how do we actually approach something like this? What we can do from specifically, I can actually add and subtract an n, and what that does is that we have to separate this out so that I cancel some of the terms, so we eventually are now going to end up with a difference of infinite sums. So an n minus n, positive n minus n plus 1, we separate this out, then now, and I'm also going to put this as the last term over here since, you know, affiliated with the minus. So now this infinite sum becomes, so n is equal 1, then now I have 1 divided by 2 to the power n, then times n plus 1. Then now this is subtract the infinite sum, n is equal 1 of 1 divided by 2 to the power n, then multiply by n plus 1 square, then subtract ln of 2. Okay, so this may look like a lot to intake over here. So to leave this as an exercise, we actually have to calculate this term, but again, as I said, I'll leave this as an exercise to you guys, but notice that that's actually going to converge. And you can show that this converges as well using the ratio test. And then that gives us that this is going to converge to 1 minus ln of 2. And then we're actually going to do a little bit of re-indexing. And if you take a look closely, once you perform that re-indexing, it actually gives us a double of that sum. So this is 2 multiplied by the infinite sum starting at n is equal to 2 of 1 divided by 2 to the power n, and then times n square, and now subtract ln of 2. So now with this in hand, now I'm going to move over here. So we have 1 minus ln of 2, and then I can actually separate this out a bit by doing, again, a little bit of re-indexing. So this is going to be minus 2 multiplied by the infinite sum, n is equal 1. Now I'll keep this the same as 1 divided by 2 to the power n and then n square. But we have to evaluate this for the n equals 1 term, subtract that, but that comes down to minus 1/2. And then now subtract ln of 2. Then again, this is going to equal, so this is going to be from 1 distribute the 2, so it's 1 minus 1 over here, well, negative 1 then becomes positive, so this is going to become 2. Then now add this with, and now add these two together, so now subtract 2 times ln of 2. And so what's left is that this is now if you take a look closely, this is by definition of the dilogarithm function evaluated at x equals 1/2. So this is 2, then li at order 2 of 1/2. And it comes down to the identity that is going to equal 2 minus 2 ln of 2. Multiply this 2, so it's actually going to be pi squared divided by 6. And then add this with ln square of 2. And actually, indeed, this comes down to the final answer of this double sum that we just calculated the entire time. So a lot going on here with integrals and not really a few of re-indexing, but a lot of we see is a lot of power series representation that we have to convert to just to get to make things mellow down a little bit easier, just like that. So yeah, that's pretty cool if you ask me.